Our topic for today is principles of measurement. It is widely accepted that the majority of medical decisions are supported using laboratory data. It is therefore critical that results generated by the laboratory are accurate. So, for the purpose of a clinical laboratory test, it is to evaluate the pathophysiologic condition of an individual patient to assist with diagnosis and or to monitor therapy. So this chapter addresses quality control of an analytic measurement procedure using quality control sample materials intended to simulate clinical samples from patients. So for our learning objectives, number 1, differentiate quality assurance and quality control. Number 2, identify different variables involved in the total testing process. And number 3, determine the Westgard rules in identifying errors in quality control run. Next, we have to define terms. First, analytical sensitivity. It is an ability of an analytical method to measure the smallest concentration of analyte of interest. So when we say an analyte, it refers to a substance whose chemical constituents are being measured. So for example, we have glucose, creatinine, and uric acid. Those are analytes we commonly measured in the laboratory. So in short, analytical sensitivity, it represents the smallest amount of substance in a sample that can accurately be measured by an assay. Next, we have analytical specificity. It is an ability of an analytical method to measure only the analyte of interest. So it means it refers to the ability of an analytical assay to measure on a particular substance rather than others in a sample. Next, we have diagnostic sensitivity. It is the ability of the analytical method to detect the proportion of individual with the disease. So for the formula in computing diagnostic sensitivity, it is 100 multiplied by the number of diseased individuals with positive test result over the total number of diseased individuals tested. So it means it is the percentage of person who have a given disorder and who are identified by the assay as the positive for the disorder. So for a test with 100% sensitivity, it correctly identifies all patients with the disease. So for example, a test with 80% sensitivity, it only detects 80% of patients with the disease or the true positive patients, but 20% of patients with the disease go undetected or the false negative patients. Next, we have diagnostic specificity. It is the ability of the analytical method to detect the proportion of individuals without the disease. So for the formula in computing diagnostic specificity, it is 100 multiplied by the number of individuals without the disease or the individuals with negative test result over the total number of individuals tested without the disease. So it means diagnostic specificity, it is the percentage of person who do not have a given condition and who are identified by the assay as negative for the condition. So for example, a test with 90% specificity will correctly return a negative result for 90% of people who do not have the disease or the true negative patients, but will return a false positive for 10% of the people who do not have the disease and should have tested negative. So for the terms in sensitivity and specificity, we use the requisite adjectives because diagnostic and analytical meanings of these terms are very different. Next, we have accuracy and precision. For accuracy, it refers to the nearness of assayed value to the true value. So it means it refers to the degree of agreement between a measured value and its true value. So for accuracy, it is the comparison of the measured value to the known value obtained from a reference material. So for example, we have the measured value and the true value. So in laboratory, you obtained a weigh measurement of 5 grams for a given substance, but the actual or the known or the true value of that substance is 10 grams. So in this case, your measurement is not close to the known value or the true value. Your measurement of 5 grams is not close to the true value or the known value. Then your measurement is not accurate. So in short, accuracy, it is an indication of how close the answer obtained or the measured value lies to the true value. Next, we have precision. Precision, it refers to the agreement between replicate measurements. So, other name of precision, it is the reproducibility or repeatability. So for example, you weigh a given substance 5 times and you get 3 grams each time. Then your measurement is very precise. Precision is independent of accuracy. You can be very precise but inaccurate, and you can also be accurate but imprecise. So in short, precision, it indicates how close the single values are to one another and is expressed by the standard deviation. The smaller the standard deviation, the more precise the values are. Next, we have delta check. Delta check, it is the difference between two consecutive measurements of the same analytes on the same individual. So delta check, it is the most commonly used patient-based quality control technique in the laboratory. So in delta checking, we compare the current result of the patient with the past results. So that is delta check. Next, we have interference. Interference, it is defined as a cause of medically significant difference in the measured test result due to another component or property of the sample. So for example, compounds introduced during patient treatment like drugs, plasma expanders, and anticoagulants, these can affect the individual's laboratory results. Next, we have tools needed to achieve accuracy. First, we have blank. It is used to cancel out or zero out the absorbance of all other components in the sample except the component whose absorbance is to be measured. So we use blanking to calibrate the machine or the spectrophotometer readings. It is analogous to zeroing a scale before weighing. So we have 3 types of blank. We have water blank, reagent blank, and sample blank. First, water blank, we use water blank if all reagents are colorless. Next, we have reagent blank. We use reagent blank to correct the absorbance caused by the color of the reagents. Next, we have sample blank. We use sample blank to correct for the potential error or the existing color or turbidity in the sample before reagents are added. So for example, we have icteric sample. For icteric sample, we need to cancel out or zero out the potential error from existing color of the sample. That is sample blank. Next, we have standard. It is a solution that contains a specified concentration of a parameter, such as creatinine, uric acid, or glucose. When a standard solution is used in place of a sample and tested, the result should match the concentration of the standard. A matching result will give confidence that the test is working correctly. We use standard to calibrate and standardize instrument in order to measure other solutions of unknown concentrations. So for the properties of standard, it is 100% pure substance, accurately weighed and prepared, certified by professional organizations, and it is used as reference material for unknown. Next, tools needed to monitor precision. We have control. Control, it is a substance or material of determined value used to monitor the accuracy or precision of the test. In order to assure that a test run is valid and results are reliable, quality control samples should be used in the performance of each assay. So how do we run quality control? It should be treated in the exact same manner as the test samples. For the ideal properties of control, it resembles appropriate human samples, stable for prolonged periods, disease-free, known analyte concentration, convenient packaging for easy dispensing and storage, and last, it should be inexpensive. For the objective of quality control, it is used to check the stability of the machine, to check the quality of reagents, and to check if there is technical errors. Next, we have types of control. We have two types of control. We have the pool serum control and commercial control. For the pool serum control, it is a serum obtained from a number of individuals. So we have human and animal. For human pool serum control, it is the most preferred since it closely resembles patient samples, but it is more expensive compared to animal pool serum control. For animal, we use bovine serum as the most common animal source. So we also use cow, goat, and sheep for animal pool serum control. Next, for commercial control, it is usually lyophilized or powdered form for stability. So it requires reconstitution. We usually use distilled water for reconstitution. Take note, incorrect mixing results to incorrect control values. So we have two types of commercial control. We have assayed and unassayed. For assayed, it is more expensive. Manufacturer analyze control and establish reference range at 2 SD values. So for unassayed, it has no values. So since it has no values, medtech needs to get the reference range of the control value. Next, we have the reference range. It is the range of values for a given constituent in healthy individuals. It is also the range of values one would expect in a defined population with no apparent clinical problems. So we need to be able to define clearly what values are consistent with health and what changes in analytical values constitute movement into a pathologic state. Next, application of reference range. Data can be distributed or spread out in different ways. It can spread out more on the right side of the graph or on the left side of the histogram, or it can be all jumbled up on the histogram. But there are many cases where the data tends to be around a central value with no bias, like this one, the yellow histogram. The yellow histogram shows that some of the data follows it closely but not perfectly, which is usual in dataset. So let's say the data is normally distributed. If this is the average or the mean of the dataset, 50% of the values is less than the mean, and 50% of the values is greater than the mean. Next, we have the Gaussian distribution curve. So it is introduced by Johann F. Gauss, and it will help us determine the reference value of the data that we are measuring. So the Gaussian distribution curve, it is also known as the bell-shaped curve or the normal distribution curve. So for the total area of the Gaussian distribution curve or the normal distribution curve, it is 100. So for a normal distribution, if this is our mean, 68.26% or 68% of the observation are within the positive negative 1 SD, and 95.44% are within the positive negative 2 SD from the mean, and 99.74% are within the positive negative 3 SD. Next, we have the mean and the standard deviation are the two parameters that fully determine the shape of the normal distribution curve. First, we have the mean. Mean, it is the average of all the values in the population. So the mean is calculated by adding the values together and then dividing by the number of values in the set. So the mean, it is also denoted as the X bar. So given the data set, let's compute for the mean. So 18 plus 18.1 plus 18 plus 17.9 plus 18 plus 17.8 plus 18.1 plus 18 plus 18.2 plus 17.9, we get 180. So for the mean, for the summation of x, we have 180 divided by the total number of values in the data set. So we have 10. So therefore, mean is equals to 18. Next, we have the standard deviation. So in computing the standard deviation, first we have to work out the mean. Since we already have the value of our mean, which is 18, next we have to subtract each number from the mean and square the result. So we have 18 as our mean. So we subtract 18 from the values. So 18 minus 18, which is 0, then we square the result, which is 0. Next, we have 18 minus 18.1 is equals to negative 0.1. Then we square the result, it is 0.01. So after we subtracted all the values from the mean, we sum up all the squared results. So 0 plus 0.01 plus 0 plus 0.01 plus 0 plus 0.04 plus 0.01 plus 0 plus 0.04 plus 0.01, it is 0.12. So let's substitute our values. So standard deviation is equals to the square root of summation of mean minus x squared. So we have 0.12 over 10 minus 1, so 9. So we have standard deviation of 0.115 or equals to 0.12. Next, to get our standard deviation, our first SD, second SD, and third SD, we have to add and subtract our standard deviation from our mean. So for our mean, it is 18, and our standard deviation, it is 0.12. So for our first SD, we have 18 plus minus 0.12. It is equals to 17, 17.88 to 18.12. Next, for our 2SD, we have 18 plus minus 0.24. This equals to 17.76 to 18.24. For our third SD, we have 18 plus minus 0.36. This equals to 17.64 to 18.36. Next, we have factors affecting the reference range. First, we have age. Under the age, we have enzyme levels is much higher in children. So, two examples of enzyme levels that are higher in children, we have the alkaline phosphatase and creatine kinase. These two enzymes increases due to skeletal growth and muscle development. Next, we have cholesterol and lipids. Cholesterol and lipids is much higher in adults compared to children. Next, we have proteins. Proteins, or the levels of proteins, decreases with age. It is because of the shift in diet or the less active lifestyle. Next, we have immunoglobulin or antibodies. It increases at birth. Next, we have sex. Uric acid is increased in males, same with testosterone, whereas estrogen and alkaline phosphatase is increased in females. For alkaline phosphatase, it is higher in females. It is because females undergo changes earlier compared to males. That is the alkaline phosphatase. Next, we have the diet. High-fat diet increases cholesterol. High-meat diet increases urea, ammonia, and urate, whereas purine-rich food increases urate. Next, we have medication. Oral contraceptive affect coagulation parameters. It induces prothrombotic state and deep vein thrombosis. Same with oral contraceptives, it increases thyroid hormone level. So for the thyroid hormone level, it contains estrogen. So estrogen causes more thyroid hormone to be bound to proteins in your blood, making them less readily available for your body to use. That is why it increases thyroid hormone in your bloodstream. Next, we have physical activity. For physical activity, there is a markedly increase of albumin after exercise. So there is a relative increase due to loss of body fluids after exercise. Next, we have creatine kinase. Creatine kinase increases after intense exercise. So strenuous exercise that damages skeletal muscles result in increased total serum of creatine kinase. Next, creatine kinase decreases in persons who are not physically active. Next, we have pregnancy. In pregnant women, there is a marked increase of uric acid, cholesterol, cortisol, alkaline phosphatase, and LDH, and there is a slightly decrease of calcium and glucose. Next, for the personal habits, smoking increases fatty acid and CEA, the carcinoembryonic antigen, whereas gamma-glutamyl transferase increases in alcoholics. Next, we have the body weight. Increased weight increases uric acid and cortisol. For obese individual, there is a marked decrease of testosterone in males and increased estradiol and estrone in women and decrease of thyroid hormones. Next, we have quality control and quality assurance. First, for the quality assurance, it is defined as part of quality management focused on providing confidence that quality requirements will be fulfilled. So, in quality assurance, it encompasses all three phases of laboratory testing. So, for the three phases of laboratory testing, we have the pre analytical phase, the analytical phase, and the post analytical phase. So, quality assurance, it is a systematic action necessary to provide adequate confidence that laboratory services will satisfy the given medical needs for patient care. So that is quality assurance. Next, we have quality control. For quality control, it is a systematic monitoring of analytic phase in order to detect analytic errors that occur during analysis and ultimately prevent the reporting of incorrect patient test results. So for quality control, it focuses only on the analytic phase. Whereas in your quality assurance, it encompasses all three phases of laboratory testing. We have the pre-analytic, the analytic, and the post-analytical phase. Next, for the total testing process. So we have three phases in the testing process. First, we have the pre-analytical phase. Pre-analytical phase, it occurs first in the laboratory process. So it is the phase where the laboratory has no direct contact in the process. So it means it is difficult to monitor and control because most occur outside the laboratory. So for the factors of pre-analytical variables, we have test ordering, patient identification, and patient preparation. Same with specimen collection, handling, and transport. Next, we have the analytical phase. Analytical phase, it is the actual laboratory testing or the diagnostic procedures, processes, and products that ultimately provide results. So for the example of analytical variables, we have specimen analysis, commercial controls or the running of commercial controls, and record keeping. Next, we have the post-analytical phase. Variables in post-analytical phase involve report generation and delivery, as well as interpretation of results and subsequent action generally experience fewer and less severe quality problems. So errors in this phase has decreased greatly because of automation and computer-generated patient results. So for example of post-analytical variables, we have reporting out specimen results and physician contact. Next, we have the control charts. Control charts is used to evaluate whether a process is operating within expectations relative to some measured values. So as long as the values fall within the upper and lower limits, then the process is in control. So how to prepare a control chart? First, obtain at least 20 control values. Then calculate the mean and the standard deviation. Next, calculate the confidence limit, which is the 95% or the two positive negative ST. And lastly, plot the control values on the y-axis against time on the x-axis. So for the Levy-Jennings plot, it is also known as the Shewhart Levy-Jennings plot. It is the most common intra-laboratory quality control chart used in clinical laboratories, and it is considered as the Gaussian distribution chart on its side. Next, we have the Westgard rules. Westgard rules are developed to improve quality monitoring, decrease subjectivity in data analysis, and to provide help in troubleshooting. So first example of Westgard rules, we have the 13S violation. It is when one control value exceeds positive or negative 3SD from the mean. So that is the 13S violation. Next, we have the 12S violation. It is also known as the warning sign. So it happens when one control value exceeds positive or negative 2SD from the mean. So one control value exceeds either on positive 2SD or negative 2SD from the mean. Next, we have the 22S violation. It is when two consecutive values exceed the same limit either on the positive 2SD or negative 2SD. Next, we have the R4S rule violation. It is when one control measurement in a group exceeds the positive 2SD and another exceeds the negative 2SD. That is the R4S rule violation. Next, we have the 41S rule violation. So it happens if four consecutive control values exceed either positive 1SD or negative 1SD. So the value must all be in the same direction. It is either on the negative side of the mean or the positive side of the mean. Next, we have the 10x rule violation. It happens when 10 consecutive control results all lie on the same side of the mean. Next, we have the multi-rule quality control. So in manual application, presence of 12S, it is the warning sign. 12S, it is the warning sign, so it triggers the application of the other rules. Thus, anytime a single measurement exceeds 2SD or either positive or negative 2SD control limit, you respond by inspecting the control data using the other results. So it means presence of 12S warning rule. It doesn't mean you need to stop your analysis, but it means you have to look carefully before proceeding your analysis. Next, how to inspect other control points. First, stop. Stop if a single point exceeds a 3SD limit, or stop if two single points in a row exceeds the 2SD limits. That is your 22S violation. Next, stop if one point in a row or one point in the group exceeds a positive 2SD limit and the another exceeds a negative 2SD limit. That is your R4S violation. Next, for the 41S and the 10x rule violation, it must be used across runs in order to get the number of control measurements needed to apply these rules. That is your 41S violation and the 10x violation. Next, we have shift and trend. So for the shift, 6 or more values on one side of the mean but maintain a constant level. So it means if this is your mean, 6 control values on one side of the mean for 6 consecutive days. So it means 6 control values on one side of the mean for 6 consecutive days refers as shift. So for the main causes of shift, it is improper calibration of the instrument and deterioration of standards. Next, we have trend. It is when control values that increases or decreases over a period of 6 consecutive days. So it means if this is your mean, 6 values that increases or decreases for 6 consecutive days. So it means 1, 2, 3, 4, 5, 6. So it means 6 values for 6 consecutive days that either increases or decreases, and that is your trend. So for the main causes of trend, we have deterioration of reagents and deterioration of light source of the spectrophotometer. Next, we have two types of error. We have the random error and the systematic error. So for the random error, we have no means of predicting the random error. So it occurs once, it is non-repeating, it is easy to spot, and usually it is a human error. So we have 12S, 13S, and R4S violation for random errors. So example of random errors, we have mislabeling of samples, improper mixing of sample and reagent, improper pipetting technique, voltage fluctuation, and temperature fluctuation. So for systematic error, it is repeating. It will be seen as a trend in a data. So example of systematic error, we have the 22S, the 41S, and the 10x rule violation. So for the main causes of systematic error, we have improper calibration, deterioration of reagents, sample instability, instrument drift, changes in the standard material. So that is your systematic error. Next, we have proficiency testing. So accrediting agencies send unknown samples in the laboratory facilities. So here in the Philippines, we have NECWAS, or the National External Quality Assurance Scheme. So information is provided on reconstitution of the samples and the assay to be performed. So after the analyses are carried out, the results are mailed back to the agency for comparison with those from other laboratories involved in the program. So proficiency testing allows each laboratory to compare and evaluate test results or outcomes with those laboratories that uses the same methods. So data are returned to the laboratory with comments and recommendations. So the ultimate goal of proficiency testing is to ensure our clinicians that patients' results are accurate. So that ends our topic. Thank you.